Let's begin with question number 3 from this OMK 2021. That is the Malaysian National Mathematical Olympiad Mathematical Bangsa 2021. Question number 3. Okay, let's read first. Given PA and PB are two tangent lines of the circle from a point P outside the circle, and A and B are the contact points. PD is the secant line, and it intersects the circle at C and D. BF is parallel to PA and meets the lines AC and ED at E and F respectively. Given the length of BF is 8, find the length of BE. Okay, now let's take a look at a diagram that I've sketched. Ta-da! Okay, here we are. I have this diagram. So let's change the screen to that. And it's a very brilliant question. Took me quite some number of days. It's like couldn't really see what was the trick here for some time. Thank God. I think this might be it. Okay, let's have a look at it. Any mistake in the solution is purely mine. Please take note. So I don't have the official answer or solutions. I'm just doing it from what I tried myself. Okay, by God's grace. Okay, let's continue on this. So P is a point outside and just the tangents like that. And then you all know that the alternate segment theorem. So let's call the angle PAC like this alpha. So, and then it will equal to ADC down here. And also that also equal to alpha, and ADC and ABC are also alpha, being the arc angle on the same arc AC. So this is how these angles marked alpha are labeled. And then now how about the angle marked beta? So let's say we talk about the other side of the tangent. So taking the chord CB here and looking at the triangle CBD with respect to the angle PBC or beta here. So again, the alternate segment theorem, and that will give the angle beta at CDB. So this is also beta, and then this can also equal to CAB, angle at the same arc CB as beta. Okay, so this is how the beta is, the markings and all that. All right. Now, being that said, so now we know alpha and beta clearly. So the diagram is being marked like this. So what about the other markings of the diagram? Like for example, we have since this part is a parallel line, PA is parallel to BF given as per definition. So this angle alpha or PAE will be the same as the alternate angles, right? So this one will be angle AEB. So this is alpha. So in triangle AEB, later will be useful, this part. So also talk about one or two more angles here. So the parallel line assures that this is alpha plus beta, PAB. From here to here, it should also equals to PBF, which is also alpha plus beta. Okay. And at the same time, we also have this side as alpha plus beta. And which is it? This one. Okay, why is this alpha plus beta? That means the angle AMB. So the angle AMB is alpha plus beta as well, because it is equals to angle ADB, which is alpha plus beta. So being the angle on the same arc AB. Can you see that? Same arc AB and circle. So that's how we get this alpha plus beta marked on the picture. Now, what's the consequence of all of these things? So there are a few remarkable things that are kind of hidden at this point from this picture, even with these markings on it. One of the first things, I didn't mark it there because I wanted to show it like this. Please take note. Let's say we join the AD and DM here. DM here. Let's look at this angle, please. This angle in the triangle FDM is the same as the angle in the triangle ADM. Sorry, same angle, sorry, not triangle, the other one doesn't matter, but if you take it like that. And what is the important thing here is this one will equals to ABM now, angle ABM, because when you say it's angle ABM, angle in same arc AM. Okay, you wonder what is this point M? Sorry, I didn't mention that. The point M is just an extension of BF to meet the circle again at M. So it's a point not given in the question, which I defined. Okay. So BF parallel to PA, that's we assume the tangent line is parallel like that. And these two lines are parallel like this. So it meets the circle again, F extended meets it at M. So we see these two are same. So in other words, we know that ABM is alpha plus beta by the earlier argument, the parallel line thing, Z is now. Okay. So FDM is alpha plus beta. And that's kind of remarkable because if FDM is alpha plus beta, if I mark it here, so we can see something there. That is in this triangle. So I'm just going to draw the triangle a little bit. Please take note. So a triangle BDM. So that is why the point of M is kind of fascinating. If we did not define M, we can't do this solution. Okay, I don't know if there's another, but it's pretty sure that the M is playing an important role, which we have to find or define by ourselves. That's what makes geometry a little bit hard sometimes. Imagine configurations of points which are not spoken of. So let's say this is point F here, as you can see. So now what we have proven is this is alpha plus beta. But we already know BDF on this side is alpha plus beta as well, as argued earlier. So that means this is an angle bisector. Okay, whenever we have an angle bisector, DF is an angle bisector. And in this triangle, so whenever angle bisector exists, we can do a ratio. Okay, it's kind of simple to see that. Actually, it's a famous theorem, is that BD, let's say we take BD like this, BD over DM, so just two, right? So you can write it like BD over DM like that will be equal to, in that order, you can see that it must equals to BF over MF. I'm just simply putting arrows just to mark it. It's nothing, not a vector or anything like that. BF over MF. Okay, this is the angle dissector theorem. Okay, so we don't need to prove these theorems when we use them in advanced Olympiads like this. We just quote and use them. The standard proof, pretty sure you can find in from the Google itself. Okay, BD over DM equals to BF over MF. So what's the use of this? So we rewrite it a little bit. Let's rewrite it a little bit, please. So BD equals to DM over MF. DM over MF, and this is multiplied by the BF part. Okay, please remember that in the given question, they gave BF equals to 8. Okay, later we'll use this fact in a while. So the DM over MF, if you look at it, DM over MF, this also is a very famous configuration of similar triangles. Sometimes you'll see it quite prevalent in some contests and Olympiads and all. So I look for something like this. Okay, let's have a closer look at that, please. Because there's a circle here. That's what makes this one as a pair of similar triangles. So they're intersecting at this point here. Let me just label that, please. So what am I talking about? This is F, F and M. So the point M is a created point. So we don't want to link it to that. We want to link it to some of the original points in the question. So this is where it leads. I'm doing it quite naturally. So I'm just going to do some coloring now. See, the opposite, vertically opposite angles in a triangle, across two lines they intersect equal. That's why these two are yellow angles. Let's call it like that. Simple. Let's not make it too complicated. So on the diagram, if you notice that ABDM, there's a circle going through all 4 points, the given circle itself. And it's like a big, nice circle going through. So these points are all cyclic. Okay, what's the use of that? So the use of that, it causes these two triangles to be similar. So a similar triangle is kind of interesting because it makes some ratios same. I mean, we can translate it to one of the known lengths as the ratio. And for example, this angle at the same arc BD, so you can compare the picture and see these two are equal. And then on this side is that alpha plus beta thing. This is the alpha plus beta here, remember? Just now we just talked about it. It's also equal to this corner here. So you can see that the three angles in these triangles are equal. That means if they're equiangular or similar triangles, we say, so we can write it in order, means let's say DFM. So when you write DFM, you're talking about similarity in the order of red, yellow, green. So the other one, you have to write the same way the letters. The red vertex now is B, yellow is F, green is A. So DFM is similar to BFA. So from which we get something called the corresponding ratio. So when we can take a corresponding ratio, that means we can say that in this case, because I'm keeping in mind the original expression there, DM over MF, I know it's sides of this triangle. So that is why when we choose DM here over MF, so that means how do we choose the points on the corresponding similar triangles here? If the letters are written correctly, first and last point, DM. So this side, I must choose first and last point, BA. DM is like BA on that triangle. And then FM would be, okay, FM is, or MF, this two. Aha. So I can say it as AF. MF is AF. Can you see that? So in other words, this ratio is actually same as BA over AF. So I'm just going to change this here and write it here now. So this part, the middle here, so we can write it as BA over AF. Okay, and then this is BF, just copy that loose. And then now I'm going to talk about something interesting because this length AB seem to be occurring. They're playing around with it. So let the AB, let's say we just use a single letter for simplicity, be X. So I look at it, then I realize this is like something like X. This is X. This is, sorry, just change the color a bit. This is AF, the denominator. And the BF is given as 8. Remember, that's the only length that is given in the question. Sorry. I don't want AB as X, sorry. I want to call AB as 2X. Why I want to modify it as 2X, later I'll tell. Just realized that. Kind of. This thing later I'll tell why. Okay. Let's just call it 2X. You can call it anything. You can just call it 2X or X and all that. Doesn't matter actually. Just to make things nice, we call it X. Because of this diagram, in case you're wondering, it's down here. The diagram is just beside on the same page here. Down here, I call, because I already call AB as 2X here by calling this midpoint. M is a midpoint, just not M, it should be N, because M is just there. Sorry about that. So this is a midpoint. Later, I'll tell you how it links to this midpoint thing. Okay, it's a little bit complicated. It's a bit of a heavy geometry. Okay, so when we simplify this, we get something like BD equals to 16X over AF. So from all of this, what I want to deduce is this fact. This is the major thing from here. This is the only thing I want to deduce from here, which is BD, strange thing to, what do you say, to work on, but later you'll see the reasons why. Slowly it'll make sense. Right now, it seems like just hunting for some information. BD times AF is 16X. Okay, BD times AF or FA is 16X. So I'm just going to take a bit of a screen grab for that part alone. So please remember that. Okay, this part. So the rest I'm going to clear. Okay, that's the first part of this solution. Okay, so give me a minute, please. Okay, let me get a screen grab. This is like solution part 1. Just save it as well. Okay, so you digest the next part. Please take a look at the what we're going to do next on the 2 pictures there. How are we going to link that, and why is that we're looking? Drawing is there. These kind of things. So it's, as I said, this is not an what we say, an easy question. It's a little bit of a tough question. Okay, I must say that. Wait, let me just save this. Sorry, trying to figure out which folder was it at. Silly me. Okay, right, almost there. Just give me a minute. No worries. Okay. Okay, so now let's just save that particular section and continue. That means I'm only going to take this equation part. Okay, BD times AF equals to 16X. That's what we have discovered so far, where X is AB over 2, okay, the lengthwise. Okay, clear all drawings. Let's paste it here. This one is one fact up here. For the entire thing is just to prove this line. Please take note. That's why geometry can be a little bit daunting or complex. Sometimes in this hunting, we can sometimes don't find anything. Sometimes we can find something. So it depends on that. Okay, let's go for the second part, please. So what do I mean by second part here? The second part involves a deeper geometrical fact. When you look at this configuration, the PABD, actually this PD is a line called the Symmedian. So I'm going to talk a bit on it by looking at showing you all the theorem itself. So the Symmedian, it's a very powerful theorem, but it's a bit rare. So this is how it looks like. Ta-da! Okay. So what is this Symmedian thing? If you look at this proof on this page here, this is a full proof. And AD is spoken of as a Symmedian of triangle ABC. Basically, what it means is a Symmedian. The 2 facts that just one of the configurations that can create a Symmedian. So what we need is from a point P, we have 2 tangents B and C with respect to this diagram. So 90 degrees here to the center of circles, you can see. So basically means tangent, PB, PC, a tangent. And then any secant line, that means it just go through PA. Do you notice A is anywhere? And then D is the intersection of that line. As long as this happens, A is anywhere and the D cuts the other line, PDA is a straight line, you get the Symmedian configuration. So the Symmedian configuration, the line AD is the Symmedian of the triangle, or in fact, it's all the way like ADP or PA, in fact. So what Symmedian is it? It's Symmedian with respect to the triangle ABC. Okay, and then you may be wondering what is a Symmedian. Okay, Symmedian is basically, if I were to put it like this, just beside it a draw in real time. So pardon the non-straight line drawing. Yeah. Okay, a median of a triangle. To understand a Symmedian, you must think of a median of a triangle. So it's just think of it like this. It's a reflection of the median across the angle bisector. So I won't prove that part, just mention. So median means these two parts are midpoint. So it's same. AM is the median of a triangle. So that means it's joining the vertex to the midpoint. And then what happens is when you do a reflection, you can prove that. It's not hard to prove, but I'm just going to focus on the facts. So if no, it gets too heavy. You must imagine that when you go for this kind of Olympiad, it's a crude line, so it's more natural. So when you reflect across the angle bisector, let's say you get somewhere here, in a point D, I mean to reflect AD, yeah, across the angle bisector. Actually, that definition also, it's a related definition, but it's not fully necessary, if you notice, because, just to maybe I make these two a straight line so it's more clear. Sorry about that. Okay, use the straight line thingy like that. And let's just change it to green color. To this point, it's reflection across the angle bisector, probably somewhere in the middle there. Okay, what happens is, this angle is basically telling that the angle BAD, that's how they prove Symmedians. It's an equivalence. Okay, so angle BAD is the same as angle, let me just color that please, angle CAM. So the angle CAM. So angle CAM is kind of fixed because it belongs to the median. So that is the meaning of a Symmedian. So this is what they're trying to prove. They used this configuration, as you can see, the proof details there. And finally, they end up proving this part. Do you notice that? BAD equals to MAC. CAM is MAC. So whenever that happens, then you can say that AD, the line that's connecting the green line here, so AD will be the Symmedian. One of the properties of Symmedian is its reflection, so it's equal, right, in length to AM. So AD is the Symmedian. Symmedian of the triangle ABC and the angle part. So we're going to use this angle equivalence. So let's say if this was like on the picture, let's say this was beta. And then on the, it's on the picture, it's like alpha. I can't remember which side I took. Okay, then this side is beta. Then that side will be alpha as well. This is the link. This is the remarkable link we're going to use on the question. So let's just try to remember this. So where did I get this picture and proof? So just to quote the source itself, just allow me to change the screen to that first. And where is my Google? There we are. Sorry, it's not Google. Give me a minute, please. Sorry. We try to search for the Google thing. Okay, there we are. This is where I got it from. As you can see, it's brilliant.org. Then you can see wiki. It's on Symmedian. So 2 pictures and proof. So in your free time, you can read more. There's another configuration, but it's not linked to the question, how the Symmedian lines can be. So this is how you can see, like some of even the a lot of talented contests, sometimes they use this kind of rare facts, calculations, and geometry can be heavy. Geometry is a lot of memorizing, a lot of configurations. That is true. Okay, you can't escape that. Okay, let me get back to the how to use this Symmedian fact. So you can see that our configuration is a Symmedian configuration. So at the bottom here, so I'm going to say that straight away in our diagram, the PA, PB are the tangents. So you can see it's a bit of a long and difficult question. It's true. Okay, PD is the Symmedian. Is Symmedian, let's just straight away say, PD is Symmedian of triangle. In this case, is triangle ABD. This triangle ABD from the vertex D is dropped. So then I realized that, let's say I take this angle alpha. So this angle here, the vertex here is very interesting because the BAD thing just now is something like AD, this angle ADP. So angle ADP is where the Symmedian is cutting, right? Doesn't matter. I just didn't label this point like BAD kind of thing. Just now, just the alpha. So I just color here, show you how it transfers to the another diagram. So one of the hard things you can see in geometry, sometimes you link to a known configuration. So the hard diagram is at the bottom there. So you draw a new picture with that just to show it separately. You can't draw it on the same, it'd be too complicated. No, you can't. It's like overlapping and you can't see the eyes and all that. So the alpha on this side means towards the line AD with respect to line AD. So it must be on the opposite side, isn't it? Do you notice this one? This angle alpha means the Symmedian. That means the median, when you draw the same vertex D, the median, the M is somewhere in between, doesn't matter where it is. We know that by the Symmedian theorem earlier, that this will be alpha on this corner, the opposite one. So the opposite one is alpha. The total angle at the vertex D is alpha plus beta, as we can see in this picture. The remaining part due to the tangent definition there. And on this thing, since the same angle ADB in totality, so this must be beta. So that is how remarkable this alpha and beta is kind of switched. But in this lower diagram, we know that since DM is a median, that means DN, sorry, use the letter N because M is used earlier. So DN is a median here of the line AB. That means N is midpoint of AB. Oh, now it all begins to make sense. So N is midpoint of AB means, so that is why I took AB as 2x earlier. If you relate to the earlier part, 2x, so that then we can see that AN equals to BN and both are x. Okay, now what's the use of all this? Now I'm going to take a nice ratio. So I need a ratio here. So what ratio am I talking about? So you can see that the two sine rules we can apply on the two triangles that we can readily see. So sine rule in triangle B and D, and sine rule in triangle A and D separately. So if I use a B and D, we notice that theta is marked as angle B and D, and A and D is 180 minus theta, straight line up. Please assume that. Alpha and beta, you all know, just saw. And angle ABD is just compared to the diagram, is this angle is just alpha plus beta. That's how we got that. So I want to take a nice ratio of BD. So I take a length BD here over, and I want to take the length BN, BD and BN here. So BD and BN here will equate to, BD is opposite sine theta, and BN is opposite of sine alpha. You'll notice that? Sine alpha on this triangle. On the other triangle, similarly, I'm going to take the ratio of AD over AN. So AD and AN, AD is opposite sine 180 minus theta. And then in the bottom here is AN is opposite the sine beta. So what does all this tell me? Did you all notice the fact that this is BN equals to AN, both are x by definition, midpoint. That's what midpoint does. And sine theta is equal to sine 180 minus theta. So it's a shortcut to see that in a straight line, the two sides adjacent are equal. Okay, a simple trigonometric fact. So that means if you notice carefully, you can see already BD sine alpha will equal to the product of x or BN here, just cross multiply sine theta, which is the same as, by doing this movement here, and cross multiply that. So other side, AN times that is the same thing. This is just AN times sine 180, AN times, you want to write like that, sine 180 minus theta, because of these two equivalents before this. And then this is equal to, remarkably, just a fascinating thing, that it is equal to 80 multiplied by sine beta, from which now I can deduce, what can I deduce? So I can deduce that sine alpha, sorry, I write that nicely, sine alpha over sine beta, rewriting this, we realize that, oh, so sine alpha or sine beta is just AD over BD. Okay, let's just keep that equation out. So I'm just going to crop this and move to the, probably the almost the last point there. One more secret hidden in this geometrical configuration, and we shall be able to compute the value that is needed in this. Okay, just going to clear all this up. Please take note. Just bring that equation only. So far we have proven this as well. Okay, now how to end all this? Okay, the Symmedian gives that. The other one, we got it from the similar triangle and some circular things, angle chasing and all that. So this is one fact. It's the second fact. Let's go to the third and final fact that we need to kind of like merge all this to do it, which is the power of a point. Okay, this is a very powerful theorem. It's also linked to a similar triangle. So some of this you have to research yourselves a bit, because I can't do it in one go like that. It's too complicated. Okay, or maybe in the future, if I have time, I'll try to this thing doubling. Okay, so if you notice carefully, this part, this is a very interesting triangle. Revisiting that, we realize that this one, this alpha plus beta, the triangle ADM. So I'm just going to draw it a little bit, if you don't mind. So please take note down here. Let's say I draw the triangle ADM. Again, remember the point M was invented by us as a continuing intersection of BF to meet the circle again. See how powerful the point is, which was hidden. So here, this is A. Please take note, this is D, and then we have an M here, right? Okay, if you remember the ADM we proved earlier, just rewind the video if needed to see that ADM is alpha plus beta. And then there's another thing here. So I'm going to take the straight line and put the point F just along this line one. So it's an F here. So we have to mark that as well. And what is the use of this configuration? Aha, some of you may be thinking, what's the point of this? So this is alpha plus beta as well up here. Okay, this is a tangent, kind of like a, we're going to do a tangent configuration, isn't it? Okay, wondering what am I talking about? If you look at it carefully, the reverse or the converse of the theorem is also true. That is, if you have alpha plus beta there, and this thing, the power, see, the power of a point, this a circumcircle, that means that there's a circle like going through here. I don't know if you can see it. Let's say we put a circle going through like this. Aha, this is the alternate segment theorem. So the alternate segment theorem in reverse is also true. Depends, we can match the point in this case. Segment theorem tells me that because the this angle, like it touches this side, then opposite inside is equal, means FDM as a circumcircle, tells me that, in other words, AM is a tangent. So AM is tangent to the, it's a powerful statement, to the circumcircle. Okay, let me write this a bit. Circumcircle of triangle FDM. Okay, AM is tangent to the circumcircle thing. So the powerful thing about that is, then we use the power of A with respect to this circle. Let's say we call it tau 1, tau lah. Okay, so it's kind of simple. I think we call it something like that. Sometimes, hazy a bit on my memory on that. So power of A with respect to the circle tau. So power of a point. Okay, we're taking a power of a point theorem. So power of a point theorem says that, okay, the power of A will be fixed. That means you take A, it's going to intersect at F and D, right? So you take the AF, product of AF, so let me write that nicely, please, sorry. So AF multiplied by AD, or you can even use similar triangles, it doesn't matter, the same thing, equals to, the tangent point means equals to the square of the, okay, AM times second intersection AM. So AM times AM or AM square. So this is another hidden consequence. So this is the other thing that we need. But if you look at the AM square, now I'm going to tell something about AM. I don't know if you all noticed that from the start. Now I'm going to say something and change this a little bit. If you look at AM, it's actually alpha plus beta, right? The angle AMB. Recall that, recap. Angle AMB was equals to alpha plus beta because it is equals to the angle the same arc AB with just one, ADB. Just to recap, these two are same. At the same time, we also know that the parallel line, see the consequence of the parallel line, PA being parallel to BF causes PAB to equals to ABF. Okay, angle ABF. Okay, ABF, if you just notice the ABF because it's just an extension, so it's just ABM because BFM are on a straight line. So that means the triangle ABM is isosceles. It's not just isosceles, it's remarkably isosceles with that AB thing for 2x, remember the definition just now, equals to AM. AB equals to AM. So that means I can just rewrite the above with this as, okay, let's just write it again. So AF multiplied by AD equals to AB square. Or in other words, I just changed this, AF times AD equals to, okay, this one equals to 2x whole thing square. That means it's 4x square. So in other words, this became just 4x square because AB is 2x. Okay, let me just take a nice screen grab of this, please. At this point, 1 minute, please. Just take this. Ta-da. So just the fact from the PowerPoint and all that. Okay, let's clear this and end the proof. Now I think we have enough things to compute the thing. Just one more thing only. All right, let me just do it as quickly as I can so that it doesn't get too draggy. Hopefully. So we have this, let's just paste it there. And one last thing, and then we are done. So if we look at the triangle ABE, one final thing. Ta-da! Triangle ABE in picture. So I'll just do a quick sketch like that. Doesn't matter, it's just a sketch. If you notice, this corner was alpha because the parallel line thing. This corner is beta due to the definition and all that, tangent, alternate angle segment theorem and all that. So up here is A, this is E, just recapping. Sorry, the E looks horrible. This is an E and this is a B, yeah, this corner. Okay, so we use a sine rule now. Aha. Remember that AB is 2x by definition. That is, I'll just mark. And they ask you to find this in the question. Huh? So we use a sine rule in this triangle. Sine rule tells me that then BE over sine beta equals to AB over sine alpha. But AB is 2x, so 2x over sine alpha. So I just rewrite this. So BE equals to, in other words, just a ratio of sine beta multiplied by sine alpha multiplied by x, and then times 2. The corner they got 2x, huh? Please take note. So it's times 2 like that. And this ratio is actually a constant. That's how we're going to prove using these ones, the 3 things here. So how do we modify from that? I'm going to take from here. The green one, please take note. Just one, take the middle info. If you notice carefully, I'm just writing it upside down. So sine beta, because it occurs like that in reverse, is going to be upside down, BD over AD. So what I do is, I just extend an algebraic trick. I multiply by a constant AF. So you multiply AF up and down. So it's still the same thing. So BD times AF, the upper part, I just choose the 16x from the earlier proof. Aha. And then the AD times AF, I take the pink color proof. That means the one we just did here. This is the last one before this. Ta-da. So it goes down like this. So this is 4x squared. Aha. So 4x squared like that. And when you simplify this, please take note, what does it become? So 16x over this thing, you become 4 over x, isn't it? When you simplify this. Aha. So BD sine beta over this thing, now I substitute this, please. So I'm just doing it in real time. So this becomes 4 over x with arrows. So calling equations and labeling them complicatedly. So you can see now more clearly. Then there's a pink x beside it, multiplied by a blue 2. Aha. So we have a blue 2 here, multiplied by 2 like that. You can see the x and x remarkably, it cancels off. And then what happens? 4 times 2 only. And finally, we arrive at the answer, which is BE equals to 8. That's it. Thank you.